So today I want to talk about the idea of differential equations. So at this point you should have read section 1.1 in the book. So let's start with a big picture of algebra. So consider the statement 5x plus 14 is equal to x squared. This is really a question, namely what value of x actually works in this equation. There's a particular solution, namely x is equal to -2, which you can check. And once you learn algebra, you learn techniques for actually solving this equation by yourself, at which point you can find that x equal to plus 7 is also a solution. Importantly, these equations can be used to model real life, namely, what time would that train reach Chicago? Would be a particular question you could answer using algebra. Maybe not this particular equation, but that's what algebra is about. So in general, with algebra, there's not really one technique that you can use to solve all possible equations. You have to classify problems and find solutions. Also, there are some equations, like 10 cosine of x is equal to x plus 1, that can't be solved analytically. You need to use a computer. There's going to be similar problems in differential equations as well. Okay, so that's algebra. Now let's talk about the big picture for differential equations. And differential equations is going to be tiresome to write all the time, so I'm going to write diffie-q's as shorthand for that. So one example of a differential equation is the second derivative of x is equal to minus k over m times x. Solutions of this equation are functions, x of t. There are different types of differential equations, as well as different types of techniques for solving differential equations. And we're going to learn about these different techniques as we go throughout the semester. And most importantly, we're going to use differential equations to model real-life situations that involve derivatives. So as an example, consider Alice, who retires and puts $1,000 in a bank, and in the bank it earns 5% interest. Okay, so what that means is her money, which we'll call the function m of t, obeys some differential equation, which looks like dm dt is equal to 1/20th m. There's different ways of understanding this. Analytically, what this means is we want to find a function m whose derivative is 1/20th of the original function. We could also look at this graphically, and graphically what this means is if we make a plot of money versus time, that as her money increases, the slope also increases. And so, in particular, slope is 1/20th of however much money she has. And so the slope of the graph gets steeper with time. Let's go further down this analytic path. In particular, her money, m, must satisfy the differential equation, dm dt is 1/20th m, but it also must satisfy an initial condition, which is that the initial amount of money is 1,000. So our approach to solving differential equations is first we want to find an m of t, which satisfies our differential equation, and then we want to tweak the function m to satisfy the initial condition, because our first guess is most likely not going to satisfy it. So let's make some guesses for possible functions m. M equal to 0 certainly solves the differential equation, but it doesn't solve our initial condition, so that's no good. At this point, we do a lot of guess and check, and you might come up with the function m is equal to e to the t over 20. And this does work for solving the differential equation. However, let's check the initial condition. And the initial condition is that at t equal to 0, we get 1, not 1,000. So this doesn't solve the initial condition. Okay, but aha, I've got an idea. How about e to the t over 20 plus 999? Indeed, at t equal to 0, this gives me 1,000, which solves my initial condition. But there's a problem here, which is that this function m no longer solves the differential equation. You can see this by explicitly checking both sides of the differential equation, plugging it in. dm dt and 1/20th m are not the same. Particularly, there's this extra term here. Okay, so let's try something new. Let's try m is 1,000 e to the t over 20. So first let's check that it solves the differential equation. And indeed it does. Both sides give me 50 e to the t over 20. So that's good. It satisfies condition 1. Okay, how about initial condition? Well, at t equal to 0, I get 1,000, which is my initial condition. So this also satisfies my initial condition. Excellent. So what I've done then is I've constructed a solution. M is equal to 1,000 t over 20, which is the unique solution to the problem that I have at hand. And in particular, what this solution means is that her money exponentially grows with time, which is why getting interest is so awesome. So don't worry if you didn't know how to find the solution in this particular case. We're going to come up with techniques for doing that much later. What I really want you to focus on is what it means to have a solution, that you can plug the solution into the differential equation and both sides match.